issues with communication when we implement these large graph algorithms at scale?
Thank you, David. So I'm Aydin Buluç from the Berkeley lab. For those of you who don't know where Berkeley lab is, if you go up at the Hurst Street, right in between here and the Soda Hall, you'll eventually hit the Berkeley lab. It's a multi-science laboratory funded by the Department of Energy. So today I'm going to be talking about parallel graph algorithms, parallel graph computations, and specifically I'll focus on three aspects of it: how to get high performance, how to get high productivity, and how to reduce communication, which is usually the bottleneck in these computations. Of course, a lot of people have contributed pieces of this talk. Maybe I won't even talk about those pieces, but I wanted to acknowledge all that has helped and the people who have funded this work. So graphs are dear to us for computer scientists. So graphs has been used as an abstraction for a lot of things, like compiler optimization in scientific computing to guide sparse reg solvers, or nowadays actually even iterative solvers, and computer network algorithms. But these have been an auxiliary helper in the sense that the data sets here, when you're running your compiler optimization or you're running your computer network, is not that huge because there's an inherent limit. It's how big your program is as the graph it's going to generate that you need to optimize for the compiler, right? In nature, the graphs themselves are much bigger. For example, the internet interactions or social interactions, they create huge data sets. Particularly of interest to us at the Berkeley lab are scientific data sets, where you're not really limited by the size of your data, you're limited by your computation size. If you ask a cosmologist how much of a data set he has, how much of a graph, it's like as big as I can solve, because he always wants to have more resolution. And that goes on for ecology, biology, chemistry, and so on. And I would like to make a distinction in the beginning why I'm not using MapReduce for these kind of computations. It's very personal, very open to object. So in my word of view, which of course these colors are wonderful, I'll need to look at the screen to tell before I say the red one, because there's no red. I kind of loosely classify the graph computations into two classes. One of them I call the filtering base, and these are the kind of operations where you enumerate triangles, rectangles, or you do some sort of browsing, scanning, or summarizing the data at the end, a lot of sampling, the kind of problems that can be solved by these algorithms. And you've seen some examples of those. And this is really a good fit for the MapReduce paradigm, or some database like Angelus to Sparkle even. When you go to more, I would call tightly coupled graph algorithms, where you need to traverse the edges and the vertices of graph several times to get a good to solve your problem. And examples are between a centrality, shortest paths, network flows, strongly connected components. Those are really hard to parallelize using MapReduce kind of structures. That's not to say that you can't map it. You can map every computation to every abstraction. It's just that it is harder to do, and it's probably not going to give you a lot of performance. So what is the challenges of this left section is really low arithmetic intensity, unpredictable access patterns, because when you're traversing a graph, every time you take a step, you actually don't know where you're going to go, and you determine at the runtime what your next step is going to be, and difficult to parallelize for that reason. So let me start the first part of my talk, really high performance. And it's again another personal view. We think that the linear algebraic primitives can be a good base for a big class of graph algorithms, and they would work very well. So what are those? Just as a picture, is not all of them, the ones that I would like to draw pictures of. I'm talking about computing the product of two sparse matrices, multiplying a sparse matrix with a sparse vector, and I want to underline the sparse here, doing a lot of element-wise operations between matrices, and extracting subgraphs. Of course, this is a subgraph where it would be nice to color code it to know what it is, but just use your imagination, it's some piece of it. But so, except that these are not running on your regular real numbers, and it's not the multiply and plus that you know of in the ring of real numbers. So you're allowed to arbitrarily overload the the algebraic structure that we call the semiring. For the purposes of systems, it's just like overloading the addition and multiplication and defining an identity element. And the most famous one is probably the tropical semiring, the min plus one that will let you solve shortest path problems, and the and/or one that will give you connectivity problems, and so on. I'll talk about a couple of previously unexplored semirings that are not deep, but nobody has actually looked at them. They'll let you solve a couple of different graph algorithms. And the word I use here, the Combinatorial BLAS, is the system that we've developed over the years. It's BLAS here stands for Basic Linear Algebra Subroutines. And that's the reason, because it's a bunch of basic linear algebra subroutines to do some combinatorial computations. So what does it look like? Again, not a comprehensive list. It really looks like this. Very simple sparse matrix operations. Some of them really hard to parallelize, though. Really easy to state. Multiplication of sparse matrices here. Multiplication of sparse matrix with a vector. Dense or sparse, element-wise, reductions. Referencing, I solved getting a sub-matrix. Assigning a piece. Some of you and random applications. And probably to get people a feel about how this would work in practice, I'm going to go over a simple graph algorithm, simple parallel graph algorithm. So before we move on this slide, the problem is finding a maximal independent set. That's very useful for a lot of purposes, but let's not get into that detail. A maximal independent set, first of all, an independent set is a set of vertices who are not neighbors of each other. So any two pairs within the independent set do not share an edge between them. A maximal independent set, just like the maximal matching we've been talked before, is an independent set that you can't grow by adding another vertex. It doesn't mean it's maximum. There might be a bigger independent set, but it's just once I give you the independent set, you can't grow it by adding another one. So it's not an NP-complete problem. The maximum would be. It's a very simple problem, and a sequential version actually runs in linear time. But it is sequential, and the parallel version, a very simple one due to Michael Luby, it's a randomized algorithm, works like this. So everybody in the graph, every vertex chooses a random number, and then everyone looks at its neighbors and determines the minimum among its neighbors. And if his value is smaller than all its neighbors, then he declares himself as part of the independent set. So again, you'll have a problem with the coloring. These red colors now are an independent set. And, but after that, what you can do is you can remove all of its neighbors. This looks like a repetition of the maximal matching algorithm, kind of. And because they can't be in the independent set. And now you're left with the remaining ones. You just toss another coin, boom. You'll find the complete set. So the theorem is that this will probably finish within log n rounds. And that's usually good enough. How do you implement this in a system that implements graph algorithms in the language of linear algebra? And for this particular slide, I use KDT, a knowledge discovery toolbox, which is a Python fronthand for the combinatorial BLAS that I previously talked. I just don't want to put C++ code on the slide, so I chose to use this particular version, a Python version of that. So the input is the adjacency matrix of the graph, a sparse matrix. I use this transpose because some of the algorithms will be easier to describe that way. The output is the maximal independent set. You initialize the candidates to all numbers from 1 to n, where n is the number of vertices, and you iterate over this. You first set everyone to a random number. And here's the crux. Once you do multiply this transpose of the adjacency matrix with the vector of candidates, but using a special semiring where all the multiplications, you're just selecting the second operand. For all the additions, you're just choosing the minimum. You'll see that by using the same data access pattern of matrix vector multiply, you will get an output vector which are the minimum among all the neighbors. And that's actually pretty simple to think about, because think about a column on the adjacency matrix. A column in the adjacency matrix are your incoming edges. Or this is actually symmetric. Don't worry about it. You're actually looking at your adjacency and summing up all the values in your adjacency using the minimum operation. That's about what you want, right? You want the minimum. That's how you gather the minimum operation. Very nice. Now, using this element-wise operation on the vectors, you'll figure out which one is the, if you're smaller than those minimum you get. If you're smaller, you will eventually add this new set to the maximal independence set. And the rest of the computation, again, does prune out your neighbors. But the crux is here, I have used the same operation, sparse matrix, sparse vector multiplication, twice, using different algebraic structures. I don't need to re-implement it. I just declare that the semiring is different now. And the system will take care of doing another computation, and it's just optimized once, run several times. And for another graph algorithm, you'll write a similar thing. You will never know how these things are implemented in the best way. It's the job of the expert in parallel computing. And when I remind something, it's that the vectors I'm using here in these operations are sparse. Even though they start dense, as you keep pruning them out, you'll see that they'll get sparser. So eventually, you won't be wasting computation later. So that is the crux that makes these algorithms work efficient and no worse than the canonical versions of those. What do I mean with the canonical version is the best parallel algorithm you find in your textbook for that application that doesn't use the linear algebra abstraction. And here's a short list of those I could come up with. And this slide, some of this is shamelessly stolen from Jeremy Kettner at MIT. Some of them is my additions. Breadth search, between centrality, all pair shortest paths, which I'm going to talk towards the end of my talk. Some maximal minimum spanning tree algorithms, and some maximal independent set algorithms. So in the first column, you see the canonical complexity of the algorithm, serial complexity, the linear algebra-based complexity here. In many cases, it matches the complexity of the canonical version. In the cases where it doesn't match, are precisely the ones that make a heavy use of the priority queues. And you'll see this, for example, Prim's minimum spanning tree algorithm. You need a priority queue for that. But the reason that they don't go into the language of linear algebra very well is because priority queues are inherently sequential data structures. So that's probably, there is a more fundamental reason that we can't express this in the language of linear algebra efficiently. Perhaps because they can't be efficiently mapped to parallel computing. I don't know. I don't want to sound too controversial. Hopefully somebody will match priority queues in a scalable way, not with logs or anything atomics like that. So why do we do this exercise? You can tell me, hey, I knew this. These algorithms are already complicated, and you're trying to show me that you have to map them to the linear algebra for performance, and I think I have a headache. Why do I do this? So here's a view. The textbook graph computation is data-driven. As I said, unpredictable communication patterns because you don't know what your next step is. A lot of poor locality of reference. You're traversing over edges and vertices and find great data accesses. Once you cast them into the language of linear algebra, a linear algebra operation has the same data access pattern every time you execute it. You know at every iteration what kind of the data access pattern is going to be, so you can overlap communication and computation. You can write code for expecting that. And similarly, you can look at the matrix and figure out block structures that you would not be able to see in the graph world. That lets you exploit some of the memory hierarchy things, and it helps you with parallel computing as well. And I'll actually show an example for that. So here's an example about what do I mean. So this is a graph color-coded for processes, and this is its adjacency matrix. So I am dividing this graph to 4 processors using what we call the 2-dimensional data decomposition. As you might see, this is fairly obvious how you would divide the sparse matrix for 2-dimensional data decomposition. You just drove a Cartesian grid over it, right? And it's not that obvious how I actually got this thing if I didn't see this word and I was just looking at the graph itself. There's, again, another color just got lost, of course. This is red, this is black. But believe me on that. Why do I do that? The 2-dimensional decomposition allows me to do 2 things. One of them is it actually asymptotically reduces the communication. And it reduces the number of processors that are communicating. You don't need to do any all-to-all shuffling you would need to do. All the communication is going to happen either in the processor columns or in the processor rows. And that's why the two-dimensional decomposition is the one that's used for every single entry in the top 10 of Graph 500 list, which is a benchmark that ranks supercomputers based on how fast they can do graph traversals using breadth-first search. So that's kind of an example why this might be useful. So far I've talked to you about linear algebraic primitives and why we think they're going to give us performance. I'm going to shift a little bit of gears and try to show you how you can get productivity and how you can sell the system to scientists, perhaps. I'm not going to actually go ahead and sell them, but it's a proof of concept way. And the crux will be to use high-level languages for the end user, and only spatialize pieces of those code that matter, and translate them into an efficiency language. That is, C, C++, whatever you want. So here's the software stack that we think is very scalable in the sense that you can. Let me start with what this is. We think of 3 agents that are in this world. The domain scientist is the biologist, the chemist, or astronomist that wants to use your system. He doesn't know about graphs, but he knows there's a graph problem. He heard about a few things like traversing a graph, maybe. He knows about clustering in graphs, and so on. But he doesn't know parallel computing. The graph algorithm developers are the people who understand graphs, but they don't understand parallel computing. And lastly, the parallel computing experts actually are the ones that match your given computation efficiently on a parallel computer. So what you want to do is to create a ecosystem that enables them to advance their pieces of these things independently from each other. And we think this is actually a ecosystem that does that. If you have a high-level language that gives primitives for the graph algorithms to use to write new graph algorithms and expose them to the domain scientist, this actually takes care of both of them. And then but this will use the primitives that are implemented in an efficiency language that's implemented in C using MPI for message passing between processors. And the parallel computing experts can optimize these primitives without knowing what they are used for in the algorithms. So that will create an independent advancement on all these fronts. And so Combinatorial BLAS sits here, and the KDT that I showed you, the code for maximal independence sets, sits above it. You can think of this as Fortran and MATLAB, if it's going to help. And this way, graph theory becomes the middle ground between computers and discrete structure analysis. And what this allows one to do is to achieve customizability, conceptual simplicity, and performance. And what do I mean with those? Performance is performance, I guess. Customizability is a very subtle point in the sense that when you are running a graph algorithm, almost never you want the textbook version. That is probably true, right? So when you're traversing a graph, you want to mark the vertices and edges, or you want to do a little bit of computation on those. You just don't want to go ahead and scan the whole graph and do nothing, just figure out the tree. You want to do some auxiliary computation on that. And we don't know it beforehand. It's the job of the person who is using the system that will customize these operations and run them. So you would like the person to be able to customize those. And for these purposes, that is the semiring. I can change the semiring and do another computation. And in the second one, it is the filter, which I'll describe in a second. So what I'm going to be showing is this is a historical slide. Eventually, you can get all 3 by using just-in-time compilation. Here's what I mean with a filter. Let's say a practical example. You have the email network of your company. And it has emails of everyone, management, engineers, and so on. Every email is tagged with a timestamp. And that's what we mean with attributed graphs. So every edge and vertex has an attribute. What kind of person, what time this happened, transaction happened, perhaps the length of the email, whatever. And then you would like to rank all your engineers, but only your engineers, using the email subset of that email set that happened in the last month. But you don't want to create a copy of that data set because it probably is huge. You don't want to scan all of it and create a copy, or maybe you'll change that filter. So what you do is you write two predicates. It says the vertex predicate returns true if the position is an engineer. Timed email predicate returns true if it happened within the last month. And you add those to your graph, and you run your favorite ranking algorithm between a centrality. And it finds automatically the most important engineer on the last year without creating a copy of your graph. And because every time a vertex or an edge is examined, it's thrown away during the execution. The good news about this is the algorithm developer who wrote this code doesn't know about the filters, because the runtime filters the edges at the bottommost level, and he doesn't need to know what kind of filters are added into the graph. So conceptually, all this really looks like is you have a graph, but you're really pruning the graph. You get a subgraph every time you add a filter, but except that you're not making copies. If you were making copies for every new edge filter addition, you would scan the whole data set and create another copy, and you would need to keep those copies because later you might pop them out and remove those filters. So you don't want to do that. That's exactly conceptually what we call the filtering on the fly. So what's the problem with that? Imagine who writes the filter. The person who writes the filter is usually the person who wants to run that analysis. The person who's trying to find the most influential engineer in the last month based on emails. So he's going to write the filter in a high productivity language. He's probably going to write the filter in Python. But all your system is running in a efficiency language, C++. So every time you need to filter an edge or vertex, you're doing an up call. Similarly, for when you're customizing your graph algorithms using semirings that I talked earlier. Same up call. The person who's going to write the Python semiring, and you would need to do an up call every time you're examining. Your performance drop can be as big as 80x, and then you lost all the performance that you got by going parallel and so on. And in a picture, it looks like this. I'm going to come back to the previous one. So this is the knowledge discovery toolbox algorithm. This is the combinatorial BLAS primitive. So it calls it, but every time it needs to examine an edge or vertex, it needs to go make a semiring operation, it's making an up call to Python. How do you fix this is actually fairly simple. It's a technology called SEJITS. It's not my contribution, but it fills a big gap between high performance and high productivity. It is a way of spatializing pieces of the computation using a domain-specific language. So what we did was collaborated with the SEJITS people and wrote a domain-specific language just for filters and semirings. And it introspects, translates that piece of the code so that it's linked to the application and never makes an up call. It looks like a simple solution, but it works drastically, and you can get both of the words for performance and the productivity. So the red line is if we just don't do this. You just run in Python, even if you use a high-performance engine on the back end, just because doing the up calls, your performance is over here, and the y-axis is time here. The yellow line is the efficiency layer code in combinatorial BLAS. There's a huge gap in between. By translating both the filter and the semiring using SEJITS, you get the blue line, which is good enough for our purposes. And this is the maximal independence set running on a big shared memory machine. And this is breadth-first search running on a supercomputer with 576 cores. And you're actually almost tracking your golden standard, your efficiency layer code exactly. And why this is so close, I can talk to you about that, but I don't have the time right now about it. So what did we do so far? We talked about performance, we talked about productivity, and we can get both of them. But I'm going to talk in the next 5 minutes of the last 5 minutes about communication. A few people mentioned communication costs in parallel computing, but it's only going to get worse. So how can we lower the communication cost of these primitives? That's the performance part still, but a specialized version of that. And the crux is to use some higher level primitives that we know of and implement communication avoiding versions of that. I'm not going to give you the model of computation. Probably Jim Demel will talk about this in a few days. Instead, I'm going to talk about why it's more important for graphs than probably other things like linear algebra. And that might sound controversial. One of the main reasons is for graph computations, there is not a whole lot of data reuse. So the communication starts to dominate much quicker than it happens in other pieces of highly computationally intensive codes. In most of the graph algorithms, you're just touching one vertex or an edge, and you just throw it away. So you're very badly dominated by communication. And that's a picture where we show the percentage of time spent just shuffling the data around between processors. Even if this is a very good algorithm compared to the previous algorithms, quickly around 4,000 cores, you're spending 80% of your time doing no useful work at all, just doing communication. And this is multiplying two sparse matrices that we use for graph contraction or algebraic multi-grid restriction, a couple of other graph things. But it doesn't matter. The example is just out of context. It can be anyone. So I'm just going to give you an example about how to avoid communication in one particular graph algorithm, because the other ones were a little too long to tell. It's the all-pair shortest path. So the input is a directed graph. The output is, for every pair of reachable vertices, the shortest path length, or actually the path itself, too, if you care about it. And the classical algorithm is this. The Floyd-Warshall, it's an outer loop, outer product over 1 to k. You can't change that induction sequence because that's the correctness. But you can reorder the computation in the middle. It turns out that this is not the best algorithm to get high performance in parallel computers. It looks like it's a better algorithm is due to clean, which is a recursive algorithm. And all probably that matters in this slide is that this algorithm is rich in matrix multiplication. So you do a lot of matrix multiplies, except you do it in a semiring. What that means is you're overloading the plus operations with minimum, and you're overloading the multiplications with additions. And what you will get by doing that, because you're matching their algorithm to a very important and highly optimized primitive matrix multiply, and you can come up with communication avoiding versions of that matrix multiply, you'll get this performance. So here's what I have here. This is running all pair shortest paths on a small matrix, small graph of 4,000 vertices, and another graph with 8,000 vertices. The reason of this small sizes is to show the strong scaling, because if you didn't do this trick about communication avoiding, you'll get this curve that looks like this little hill, the blue one. But as you strong scale, you get extra memory. Right? If this data fits on one compute node, when I fit it on 64, there's a lot of empty space in the memory. I can do a smart replication of the data in an algorithmic level and reduce my communication requirements. And that's exactly what this communication avoiding version does. It uses extra memory to do replication and increase performance. And you'll see by for replication, you get over here, by replication of the amount of 16, you continue scaling even for this small data set. And similarly, much better scaling for the other one. So although David tells me this, I have -2 seconds. Mine tells me I have 1.5 seconds. So that's about it. That will be hopefully a pointer for you to look at it later. Any questions?